First one is that there's my cue, actually, that we plan to post these talks, these sessions, recordings on the website on geoclash.org. We are going to be working with individual speakers on permissions, and everyone will have the opportunity to opt out. So you are not beholden to doing that, but we will work with individual speakers on that. We hope to get as many as possible up there, but we know some speakers with government and other affiliations will need some approval process. So stay tuned for that. The second announcement is that, again, don't forget, this is the first part of our modeling expo. It's going to continue in the fall with an in-person event. We are still formulating that. And if you are really excited about joining a discussion about model couplings and interactions, stay tuned for that. We're still going to be posting that to this group and others as well soon. Brian Yanites, it is your stage for talking about sediments. Thanks.
All right. So in this next session, folks, we're going to talk about sediment transport and dispersal in fluvial systems. And while it might not be the first thing you think of when we think about land surface hazards, it's actually quite a critical component when we think about the hazard cascade, right? These systems are the ones that take these point sources of sediment and then disperse them long distances and over long periods of time, and in those processes can propagate hazards throughout watersheds. Right, and so we know that there can be erosional hazards along river systems, just the entrainment of banks and impacting infrastructure and life that might be existing along the river pathways we see here in this photo from Taiwan, as well as this photo from the north side of Yellowstone from last summer. And of course, the aggregation of these river systems and from the sediment within them can also be hazardous directly, as we see in this picture in the upper right, in the Malapchi River in Nepal from a couple of summers ago, as well as in sort of a long term. This is Franz Josef in New Zealand, where the river is aggrading at something like 16 centimeters per year as glaciers retreat in the Southern Alps and overwhelm the fluvial system with sediment. You can see that this motel down here wasn't necessarily built below the riverbed on purpose. And then sort of a great example, Mount St. Helens, and I'll be a little ageist here and say I was 6 months old when Mount St. Helens erupted. And yet the Army Corps of Engineers is still spending about $10 million a year dealing with the sediment that's getting routed through the fluvial systems. And if it wasn't for this sediment retention structure, there'd be tens of thousands of people with increased flood hazard risks downstream, as well as the possibility for shutting off shipping lanes in the Columbia River and cutting off Portland from global trade routes. And so there's lots of sort of importance in thinking about that entire hazard cascade and in the spatial and temporal context of what we're trying to achieve with this modeling framework. So just a quick reminder, right? When thinking about these, we've got some talks lined up. When thinking about these talks, think about what opportunities there are for model couplings to address hazard cascades, what modeling areas need attention and the central gaps, and how modeling informs data acquisition and sensor development deployment. Feel free to use the Zoom chat or hop on the Google Docs that get posted in the chat. And at the end, after all the talks, we'll have a discussion as well. So our lineup today is, we'll start with Jon Czuba from Virginia Tech, and then Colin Phillips from Utah State, followed by Jeff Keck from the Washington DNR, and then Angel Monslave from the University of Idaho. So we'll see a sort of a wide range of modeling approaches in different parts of landscapes and different types of data that we might think about in this sort of fluvial dispersal and sediment transport. All right, I will stop sharing. Did I stop sharing? There we go. And turn it over to Jon Czuba from Virginia Tech. see.
Okay, I think everyone can see my screen well. Thanks, Brian, for the introduction. So yeah, I'm Jon Czuba. I'm in the Department of Biological Systems Engineering at Virginia Tech, really thinking about ecosystems engineering in our department. So a little different from geoscience department that a lot of folks are in. And so I'll talk about modeling sediment dynamics in river networks. And this is work that I've been thinking about for over 10 years now. And specifically, what I'll talk about today is a river network modeling framework for tracking the transport and storage dynamic of sediment as it's routed through river networks. And so the kind of key fundamentals of this model, which I'll mostly talk about and then talk a little bit about applications toward the end, is that first and foremost, you need some sort of network, here a river network, and that network can include reservoirs or ponds or lakes or something in there. There's flexibility there in terms of what those links represent. But for this modeling, it's really coded to only thinking about fluvial transport. So we're really talking about river channels up to about 1, maybe 3% slope, where there's that handoff between the debris flow runout and fluvial transport specifically. And the model's broken down into a few key elements. The one fundamental element of the model domain is a stream segment, or what we'll call a link. And that's a segment of a stream channel, usually in between tributaries. It could be smaller than that, but it needs to be some segment that you have a constant slope and width, and you can apply a certain discharge and channel properties that are consistent throughout that section of stream. That's the first thing. And the second thing is that this is a Lagrangian model, and so we're tracking individual elements of sediment. Here, we're discretizing the sediment that's being input and transported on this network, which I'm calling parcels. And each of these elements that are being input can have their own volume, their own grain size, their own lithology. We're putting them where we want to put them in space and time. And they can also have an identifying tag to say, this sediment has come from this hill slope, or, this debris flow channel, and how is that going to move through the system? So we can do more in terms of tracking and determining where things are going and how long are they taking to get to certain locations. And so to break this down a little bit more, here's just an example schematic of a conceptual network, where let's say this would be 3 different links between, this would be one link of a stream network, and then 2 more downstream, defined by the upstream and downstream ends of each link by these dots. And let's just conceptualize the sediment that's being input as these brown boxes with the different circles. And the circle size is meant to denote one of many different attributes that it might have. Here we'll talk about that being sediment size. And so in the model, what is fundamentally happening is we're looking at those sizes, and we're transporting them downstream based on a mixed grain size sand and gravel transport. We can model those sizes being anywhere from sand to gravel. We're really talking about bed material. We can get into the really fine sediment, but there's like a little bit more dynamics need to work out beyond the trivial just pushing all this fine sediment downstream as wash load. But what's happening is that for these models like this parameterization, there are some parameters that depend on the link itself, such as slope. There are other parameters that depend on the sediment parcel itself, such as grain size. And there's also the parameters that are aggregated properties of the sediment within the link, and how that is incorporated, such as what is the grain size distribution, and how do excess sediment that's in that link contribute to in-channel storage. So for instance, we would move each of these sizes downstream according to their size and relative to the characteristics of that link and the aggregated properties. And specifically here, if we have too much sediment in the link compared to some of those sediment parcels into in-channel storage, and that can then feed back into channel slope. So then we're talking about these other dynamics that are happening. And we're also looking at sediment attrition, things that don't have a lot of time to talk about. So for implementation, we define a network, we assign stream segments. This is kind of defining the characteristics. Some of the initialization steps are initializing the bed sediment, because if there's nothing there, you just have a bedrock floored channel. So you want to have some alluvial layer, perhaps to start out that model. There's ways to do that. The key ways for model coupling are these next two. One is we want to input sediment pulses in space and time in some way. So really the key things we want to get at are what are the volume inputs in space and time, and what is the grain size distribution. So models like Roman DiBiase was talking about yesterday, where you can look at hill slopes, and here's the grain size that could be brought in through these different processes. That's the kind of information we would need as the input to ingest. And then also specifying stream flow. Specifically, what's driving the model is bed shear stress. And so there's many ways to get that and to parameterize that. And so there's another way to couple to these climate models or precipitation models that can look at how those are going to propagate floods through the system, and then use that stream flow and shear stress to then move the sediment in this model. And then the model just steps forward tracking the sediment parcels, and we visualize the results. So here's one example of results, a movie where we have this post-wildfire debris flow. We have emplaced sediment from those debris flows in these channels, and we can look at over time how that sediment might be moving downstream, how it's being reworked, where are some areas where it's being trapped more than others. And then we can start looking at things like how much sediment is in what lengths of the channel. And then just going quickly, we're looking at sediment depth, bed elevation, grain size distribution, and volume in any link in the channel, and also at the downstream outlet. And we can track sediment inputs as they move through the network. Just a couple examples of model outputs. We can display things in terms of the network. Looking at the bottom two plots here, we can look at distance downstream, looking at accumulation. We can look at the outlet, how the sediment is arriving. We can look at grain size distributions in any link. We can again look at travel distance or travel time, and we can break it out by grain size that's in a different watershed, and we can look at different pathways. I know I'm out of time. The only two things I'll say is we've been coupling this with post-wildfire debris flows, working with Patrick Belmont and Brendan Fraser, and also working with Allison Pfeiffer looking at sediment attrition. I'll just say that here are a few papers that talk more about this process, and I'll end it there. But thanks for organizing this event.
Thanks a bunch, John. That was a fantastic talk and great sort of lead into thinking about these modeling approaches. Next up, we have Colin Phillips from Utah State. Colin, are you there?
I'm here.
All right. You should be able to share your screen.
All right.
There you are.
I think I will say that that was a great talk, John. And it's Brendan Murphy, not Brendan Fraser. He's at Simon Fraser. Be real interesting if it was Brendan Fraser.
Oh, yeah. I love Brendan Fraser, but sorry, I didn't notice that. Yeah.
Okay, I'll go ahead and get started here. Let me see if this gets... Everyone see that all right? Can people hear? Okay, great.
That looks good.
Okay, so title of the talk is High Resolution Channel Response to Flooding, Wildfire, and Debris Flow. And this is in collaboration with my colleague, Claire Misteller. NSF recently funded us to do some of this work. And you can sort of see three high-resolution LiDAR snapshots. The little bar on the lower left is the scale bar, same for each picture. And red is erosion, blue is deposition. So a model for sort of river geometry is this well-worn and time-tested downstream hydraulic geometry, right? River discharge increases with drainage area for the bank full flow. River width and depth increase with discharge, and velocity is roughly constant or weakly increasing, right? And those stars represent one channel going downstream, in particular, the Eel River. And so this is, I think, as I said, well-worn, time-tested, and generally sort of what rivers tend to do in aggregate. If we think about what might be controlling the underlying physics, we have what's known as sort of a threshold model, which is what the canonical canal model would be. You're at the threshold of motion everywhere. And rivers seem to follow this near threshold model, most of the time, maybe. So it means that you're able to transport sediment on the bed, you have a mobile bed, and you're at the threshold on the banks. Now, while this matches data very well, there's basically, it just gives us stability criterion. There's no prediction of variability, pace, or the process of adjustment. And when we think about hazards, when people have alluded to this, what happens when the DEM's no longer the same DEM, right? When it changes. And one of my colleague, Claro, says, well, can a river get out here? If a river, can a channel even get there? What would happen if a channel got off the curve there? So our project is really looking at one, trying to create this signal to noise framework for rivers. And can we attribute changes in river channels to specific forcing mechanisms and eventually predict how they're going to change or respond? So one is characterizing the noise. And then we would need to be able to figure out, what's an actual signal from a stochastic system. And then we're working on sort of developing that physical model to keep going through. So in this case, how variable is a river? And so we took LiDAR topography. We've got our discharge width scaling. We can extract bank lines from many different sites along here. And we can sort of put these rivers on this space and say, hey, now how variable is a point, right? There's an order of magnitude scaling or sort of variation around any given discharge, which I think from a geological perspective is not a huge problem. But I'm an engineering department, and having a factor 10 inability to predict river width is problematic for a bridge. So if we look at this, we've got specific site investigations. We can grab all of their little histograms and show that by and large, that variability at reach scale is pretty consistent and it's fairly predictable, right? And we can add some error bars to sort of our general hydraulic geometry model. Now, if we were to look at one site in high resolution, and that's sort of what we get as an advantage here, we've developed an algorithm to go in and pick out sort of the bankfold geometry as you move downstream in any LiDAR map. And so you can see that there's quite a bit of variability around the gauge prediction. And sometimes the gauge prediction, which is just based on 4 USGS gauges, is a little high. And sometimes it's pretty good. If you were to think about sort of that signal and noise framework, though, right, is 90 meters of erosion a lot? I sort of think that 90 meters is a lot. And here's the Eel River in Northern California. And you can sort of see it moving along in the satellite images over time. But that 90 meters, when you think about it from a probabilistic standpoint and the variability the channel has inherently, isn't that much, right? These bankful widths here, it's not that different. Now, 90 meters could be a lot, even in a big system like this, because proximity to society determines when change, which in this case is minor relative to the system, becomes a hazard. And you can see a major interstate right there on the side, on the left side. So that's one thing we're working on here. Now in this case, right, what about 30 meters of erosion? And here we have a fluvial test case, which is the 2013 Boulder floods. This is 4 Mile Canyon Creek. It's only 30 meters, but the channel was only about 10 meters wide at most. And so in this case, it's a huge degree of erosion, right? But one thing we noticed from this flood case is that the flood erosion is relatively uniform throughout the system. Compared to if you go to a wildfire system where you're going to get quite a bit of sediment, we see a very different change. So here's a sort of a fire that happened in Utah, burned part of it. We've got a dam upstream and a reservoir, and downstream we have a USGS gauge. So the system is fairly well constrained hydrologically. And you can see the long-term rainfall record from 1985 till now. We get a storm that is big, but not the biggest. So there's our post-fire storm, there's a fire, and before the thing really even stops smoldering, we get hit by a fairly large storm, which produces that peak on the far upper right. So here's the system pre-fire, and here's the characterization of the river geometry in terms of just width. Here's the post-fire issue. So what we notice right away is that there are segments where the river didn't change at all. Even though it was a big flood, it wasn't that big. And what we see is that often that sediment came in, and so we have 2 different kinds of hazard here. One that is just a flood hazard, and then the sediment one, which is highly localized to the debris flows. In this case, right, we can look at, say, a cross-section, and one of the interesting things is that we see, right, no change in some spots. So if you look in the upper right, you'll see this little PDF in black and PDF in blue, and it sort of shows that pre-fire and post-fire are the same in spots where you don't get sediment. But when you do have sediment come in, you get this large shift and the river sort of quadrupled in size. And in this case, one of the interesting things we saw is that the perturbation propagates upstream for the sediment, whereas the flood hazard, the perturbation propagates downstream. So in this case, right, debris flows come in, dam it up, the channel switches and avulses, and there's quite a bit of destabilization. So what we're working on, and where I think the biggest sort of open questions remain, is that, right, we've developed some tools to extract high resolution topography. We've been characterizing that variability to understand the noise. That's our project one goal, is sort of establishing this signal to noise ratio. But when we get to sort of these hazards, the sediment and the flood, that project two of sort of building in this mechanistic channel destabilization model is a huge ask. I think we know in some case the answer, right? The hazard response. We have time-lapse LiDAR. We just need to piece that middle part, and that's where I'm sort of really excited about here. Thank you.
Thank you, Colin. Next, we're going to move into Jeff Keck is going to present on mass wasting runout and assessing landslide hazard and sediment delivery to the channel network. All right, Jeff, can you share your screen?
Sorry, can you see my screen?
Yes, it's still, it hasn't been gone into slideshow mode yet.
Okay. Okay, so
there we go.
Mass waste, yeah, am I good?
Yep, you're good.
All right. Mass wasting runout. It's a new landslide runout model for landscape evolution, sediment budget, and hazard assessment applications. It was originally, I guess, conceptualized for coupling existing hill slope models with existing sediment transport models, specifically Jon's model that he just showed. We've calibrated it and tested it at a number of different landslide types and runout terrains, including this landslide in A, which was a really large landslide that completely inundated the downslope terrain, or this landslide at B, which is mostly small channel adjacent landslides. Their runout material consisted mostly of material that they entrained, and they flowed mostly as channelized debris flows, to landslides like this at C, which started as sort of a moderately sized landslide that entrained a lot of material as well, flowed down a planar slope, and then spread out on a divergent slope. So in addition to those three landslide sites, there's another three that we've calibrated and evaluated model performance to. Most of them are in Washington State, another is in Colorado. For example, that channelized debris flow site that started as small landslides was in the Olympics here in Washington, or that large debris avalanche that inundated the terrain, it's in South Washington in the Cascades. So mass wasting runout, it's coded in Python as a component for the package Landlab. And Landlab is a flexible open source modeling framework for Earth surface dynamics. I think the next presentation I saw is also going to be doing their modeling in Landlab. But the nice thing about Landlab is, one, it has grids that you can build your model on. Everything with landslide or mass wasting runout is built on the master raster model grid. And there's existing models. So like there's the shallow landslide probability model, and there's this vegetation dynamics model. So I'm going to tell you how the model is conceptualized. Imagine you're in the field. You're walking up this small channel. To your left, you've got this gentle ridge. So you get farther up the channel, you start hiking up this slope. And near the top of the slope, you come across a small landslide. The body is still on the hill slope, but there's clear indicators of movement, tension cracks, scarps, and you're concerned about the runout extent, or maybe how much sediment it's going to deliver to downslope aquatic habitat. So back in the office, you represent this in the model on a grid. The elevation, the slopes are values on that grid. The landslide itself becomes the cells that were in that polygon that you mapped in the field, with the depth you specify based on your field estimate. In the model, those two grid cells are released, and as they flow down slope, They entrain material as a function of soil thickness and the shear stress at the base of the flow. They deposit as a function of the terrain slope and a critical slope parameter. And the amount of material that leaves any one grid cell is a function of the material that came into it, minus the deposition amount, plus the entrainment amount. And we impose this rule that the material stops if it doesn't exceed this threshold flux parameter. These two parameters, SC and QSC, largely control model behavior, and we use that to calibrate it to those 6 different sites. So here's an example implementation of the model to that large debris avalanche that inundated the terrain. We have repeat LiDAR scans here, so we know how the landslide actually modified the terrain. Most of the sediment ended up down in the river. This is the modeled recreation. So in this blue is erosion. So I released all of the grid cells that were in this mapped polygon. The mapped polygon is something I created from remote sensing observations. The depth I specified from the LiDAR differencing. It's flowing down the terrain, mostly controlled by topographic slope, blue, erosion, red, big deposition depths. Most of the material ends up down in the river valley, but the behavior of the model really depends on how it's calibrated. And for calibration, we wrote an adaptive Markov Chain Monte Carlo calibration utility that automatically calibrates mass wasting runout to an observed runout data set, where the observed runout data set is that LiDAR differencing map, or if you go out in the field and you map your deposition and erosion depths, that could be used. But what you're seeing here is how the algorithm jumps in parameter space, and it eventually circles in on its best fit parameters. And one of the outputs of this algorithm is an empirical PDF for each parameter that you calibrated the model with. So we were using that critical slope and critical flux parameter. We get a PDF for each of the 6 sites. So we have those PDFs. Now I'm going to show you how to use the parameterized model to evaluate runout probability at this watershed. So with this, I'm going to couple it to that existing landslide model in Landlab, landslide probability. And the way landslide probability works is it iteratively runs the infinite slope model n times. Each iteration, it samples from a user-defined PDF for each parameter in the infinite slope model and precipitation. We can get runout probability by simply inserting mass wasting runout into this while loop. So for each of the n iterations, it runs mass wasting runout. And where before landslide probability was the number of times the factor of safety was less than 1 divided by the number of iterations, now runout probability is simply the number of times your DEM changes divided by the number of iterations. And in the same way, we can also get the probability of deposition by changing this to the number of times that you get sediment accumulation greater than 1 meter. So this I guess probability represents both unknowns in landslide size, location, as well as parameter values, which are informed by the PDFs from the calibration utility. So mass wasting runout in summary includes a calibration utility. It can be run probabilistically and it involves the terrain. And thanks for letting me talk.
Thank you, Jeff. That was very thought-provoking, interesting talk. If you anybody, just quick reminder, if you have questions for any of the speakers, put them in the chat or on the Google Doc, and after our next speaker, we can have a big sort of overall discussion. So next up, we have Angel Monslave from the University of Idaho, who's going to stay in Landlab world and talk about RiverBedDynamics.
Can you hear me okay?
Yep, can hear you, and we can see your slides.
Perfect, that's good. Well, this will be a good transition. So we keep talking about Landlab. So good day, everyone, and thank you for joining me today. My name is Angel Monsalve, and I'm a postdoctoral researcher at the with the Center for Hydraulics Research at the University of Idaho. I'm very excited about my presentation today. I'm going to present RiverBedDynamics, which is a Landlab component for computing two-dimensional sediment transport and river bed evolution. This is a collaborative work with Sim Anderson and Nicole Gasparini at the University of Tulane, and also with Elwin Jagger here at the University of Idaho. Okay, we are good. So just to give you a little bit of context of what we are doing, we created we are proposing a new landscape evolution model, or LEM, that I'll be referring often in this presentation, which is an essential tool for us, actually, because it's allow us to predict and how the landscape morphology will evolve in time under different conditions, for example, climatic, restoration, tectonic scenarios. There are a few, or not
Angel, I'm sorry to interrupt you. There's
Sure.
Some black dialogue boxes in front of your slides. Do you have any dialogue boxes open that might?
That one?
There, yeah. Well, there you go.
Sorry.
And one more, and then I think we'll be golden.
Yeah.
Thank you.
Okay. Yeah, I don't see that in my stream. I'm sorry. With most of LEMs, they differ between each other depending on the components that they include, the temporal scale in which they work, the processes they include, and also how user-friendly they are. So we are proposing this new Landlab component to basically incorporate or focus on the dynamics of the riverbed. Ideally, an LEM should include conditions about the local geology, soil conditions, weather, and catchment properties, because these are the factors that drive the water movement and control the soil movement too. But including these variables, or all these variables at a local scale, is challenging because the inputs required are difficult to get. In a mathematical point of view or numerical point of view, also most of these processes are difficult to include in an accurate way. So our new model is designed to model the evolution of gravel bed streams within a continuum framework. This means that we are not simulating the movement of the individual particles, but how volumes of sediment move. RiverBedDynamics, our new component, requires a flow solver. So we are only evolving the bed, but we need like outside information from a flow model, because we need to get the shear stress up. I'm going to talk about that in more detail later. But that's the main reason why we decided to do this in Landlab, because it's really easy to couple different models. In this case, we need a flow model to get shear stress and then move our sediment bed. However, in the models that are currently available in Landlab, most of them they don't have critical aspects that we consider that are very important. For example, they don't consider the position of sediment in a riverbed environment, and also the meaning roughness coefficient. It was considered in most of them constant in the whole watershed, and also precipitation was uniform throughout the watershed, and that for us was a little problem. So we took overland flow as a flow solver. We modified it so now it includes variable roughness, variable inputs of precipitation or discharge. We can see in this small animation, we are in the input of precipitation is only on the left side. So now we know that our model is it's working relatively, I mean, it's working well. And in the core of RiverBedDynamics, we solved the Exner equation for sediment mass conservation at a local scale. In this sense, it means on every single cell within the Landlab grid. And we use as an input the unsteady non-uniform shear stress, which considers the changes in topography, local changes in water depth, and also flow velocity. Basically, and this was explained in the previous presentation. Basically, within the Landlab environment, different models are coupled in a driver file, and you run one model, then you run another, and they start talking to each other within the time loop. That's mostly how they work. How did perform our RiverBedDynamics? When we compare predicted to analytical solutions, we got a very good results. In the left side, we have an increase in slope, so there was more sediment than the one that the system could move, and the system automatically adjusted the slope. On the right side, it's the opposite, so there wasn't a lot of sediment coming in. Compared to other, in our model, we have different bed loads transport equation that can be used, so the result can be more or less complex depending on what you need. And also we are able to track, and with this I'm going to finish, we are also able to track the changes in time and in space of the surface and subsurface grain size distribution. So this is the major difference compared to previous models. And that's it. Thank you.
Thank you, Angel. All right, so that leaves a few minutes here for general discussion. If anybody has a question, you can raise your hand. Put it in the Google Doc or the chat. I see some questions going on in there now and some answers. If I just have a general question for, I think that applies to everyone. Oh wait, here we have Nicholas Tar. Do you wanna ask your question? Oh.
Thank you. I have a general question, and I was particularly intrigued by Colin's and Jeff's talks. When the difference between what I would call aggregating flow and eroding flow, I have noticed on many of occasions that if you have a debris flow initially, a large volume of debris will produce essentially a U-shaped channel, very efficient, and it's basically viscous flow type problem. But if the debris is somehow arrested, and we have seen a perfect example here on Highway 1 south of Big Sur recently, the debris load drops, and now you have essentially clear water, turbulent water coming, and it becomes very eroding flow. And to me, that is kind of an important element of understanding whether you have erosion and erosion of the material, and basically the volume bulks up, or you have a situation where the material is deposited because it just clogs the channel, and then water becomes clear and picks up sediment further down. And the other thing, for fear of being somewhat dogmatic, when looking at these floodplains and the channels, what is the geomorphology of past? I just came back from the Andes in Peru, and the amount of downcutting since glaciation is 50 to 100 meters. And you see these deposits of previous debris flows, previous channels. So somehow that information would be valuable in terms of how we look at these processes. Anyway, that's my comment. I don't know what Jeff or Colin can add to it.
I mean, I can certainly say we're really interested in the idea of how much information can we get out of sort of the topography, without needing to necessarily have a really high resolution time series or time-lapse LiDAR, which is sort of a novel concept we saw with sort of Roman DiBiase's post-fire work. We're not going to have that everywhere. So if there's some information, we can look at the landscape and say, look, we see that this is a channel that is ready to sort of grade at an instant. That's a spot where sort of it could shoot its width quite large, or you can see sort of the past impact of debris flows or landslides and go, right, this is a channel that is probably on that threshold of instability most of the time. And then, in some spots, so anything we can get out of that, and we've been sort of looking at that in detail, though it's still sort of in its infancy. We've spent a lot of time on the algorithms to extract that high resolution. In some cases, you can really see where landslides have come in, and it shifts that sort of probability distribution and introduces a new lobe.
Building off that, I was just a general question for all the speakers, because I think it all fits all of your talks, is how do we, handle morphological changes in these sort of modeling approaches, and specifically channel width, right? Because that's going to change shear stress, and that's the, what we see change the fastest following sort of triggering hazard cascade. Anybody have any thoughts on that?
Can I share my thoughts?
Sure.
Yeah, I
Jeff
guess.
And John.
In addition to modifying the flow, whatever inputs are coming into your flow as it interacts with the terrain, you also, I guess, impose some sort of change to the terrain itself. So you evolve the terrain with, like Dr. Saklar was just mentioning, whether you have a grading flow or an eroding flow. If you have an grading flow, in that case, you've got grains that maybe more rapidly erode the terrain. And so after that flow is passed, you'd have a wider floodplain for a flood. Or if it's an eroding flow, you must have had a huge deposit form. So your channel gradient has changed. So making sure that you also evolve the terrain with the flow might help with that.
Yeah, and I'd say that.
Go ahead, John.
No. If you're talking about,
I was just going to.
Go ahead.
Sorry.
John, go.
Okay.
John, go. There you go, Brian.
So yeah, I think the easier one is to manipulate the channel bed in determining how that's going to shift in time. I think the big question, I think that's the one that Colin and I identified too in the Google Doc, is that how the width is going to change in time due to flow or aggradation. That's kind of the big unknown, and what sets the kind of geometry of channels is still a big open question in fluvial geomorphology that somehow we'd want to parameterize that moving forward, but that's certainly the big unknown here.
Yeah, I mean, I don't have an answer. One of the things that I do think about, though, is that given that, and this could be wrong, but given all of the channels that we see sort of fall on a similar scaling relationship, whether they're destabilized or well constrained, it gives us a probabilistic bound to say that maybe I can't tell you what the channel is going to be after a hazard, but I could maybe say that it can't be bigger than X and it's not going to be smaller than Y. And perhaps I can treat the problem probabilistically from there as a forecast to say, I know it's between these two end members, so I'm going to model that space sort of Monte Carlo-esque. Otherwise, I mean, I think, if we could, as Jeff was saying, have a model that could change the grid, I mean, that's the golden opportunity there. But if you're going to try to do that sort of at the scale of the national water model, every time you ask them about, hey, can we change the grid? It's daggers. They stare at you.
The last thing I just want to say to follow up with what Colin said is that I think the width is one thing, but I think the slope is the most sensitive parameter in terms of looking at transport. So I think the slope we need to get right for first order, and I think we're pretty good there. But then I think slope is going to be more important than width in terms of determining overall fluvial transport. But it is still important on how that changes.
Great. Thank you all. Thank you all to the speakers for a fantastic session. I think we really saw the emergence of cascading hazards in this session. And so I'm going to pass it over back to Josh to introduce our last session.
We are